Alright, so this PowerPoint will be covering the results of Lab 2. So the main purpose of this lab was to improve upon the data analysis of Lab 1 while also creating a better glow script model to represent the two pieces of tape. Although both Lab 1 and 2 are about using electric principles to approximate the excess charge on an object, we're now able to represent the excess charge as spread out across a surface rather than at a single point. As a result, we can more accurately find the charges on the pieces of tape. Since this lab is more focused on reworking the data that we already had, here's just a list of the values that we're going to be pulling from last week's lab, including the length of the tape, mass of the tape, the gravitational force on it, as well as the separation of the tapes to which they started to float above each other. Also, it should be noted that the force of gravity and the electric force are equal in magnitude. So here we have a diagram meant to represent the top and bottom tapes, labeled rod B and rod A respectively. Note that we use variables to represent the location of an infinitesimally small piece of each rod. This is what we're going to be using to set up our electric field equation. Since we want to find the electric field at the top tape due to the bottom tape, we can use this to set up an R vector, R magnitude, and R hat using the variables we already established. Also, since we know that the charge distribution will be Q over L dA for the bottom piece of tape, we can sub that in for Q in the electric field equation. What you see at the bottom is the end result of the integration, leaving us with an equation dependent on B, the location of the segment of the top piece of tape, which we can later on integrate to find the total electric field. So after finding the total electric field at the top tape due to the bottom tape, we can use a similar method to find the electric force. This is done by multiplying the electric field by the charge distribution of the top piece of tape, and then integrating over the bounds of B. What we're left with is an equation that represents the electric force in the positive y direction due to the distributed charges of the tapes. Now, since we know that the force of gravity and the electric force have to be equal in magnitude, we can rearrange the numbers to give an expression for Q. And using the values we measured from the previous lab that are also listed in an earlier slide, we find that the charged tapes have a charge of 2.875 times 10 to the negative 8th coulombs. Here's a picture for the computational model for this lab. The code works by doing what is essentially integration by dividing the tapes into n pieces and finding the net electric force. However, if you look up top, you can see that for this model we're actually using a slightly higher value for the charge of the tapes. This is done because the tape is only split up into 30 segments, whereas integration accounts for an infinite amount of small segments. In this scenario, for the electric and gravitational forces to be equal, the charge must be slightly increased. On this model, we've changed nothing but the charge, correcting it to the value we previously found. Pay attention to what happens to the forces in the dialog box. When the tapes are only broken into 30 pieces, we can see that the charge we found doesn't seem to be all that accurate. However, as we increase the number of pieces that the tapes are broken into, in this case 100, we can see that the forces do become more similar. When the tapes are broken into 1,000 pieces, we've reached a point where we are off by less than 1%. And when we break the tape into 5,000 pieces, we can see that the two forces are almost exactly the same. The main takeaway from this is that as we increase the number of pieces that the tape is broken into, these numbers will eventually be exactly the same. As far as conclusions from the glow script model, we conclude that as we increase the number of pieces that the tape is broken into when analyzing the model, we find that in order for the gravitational force and electric force to be equal, the tapes must have a charge of 2.875 times 10 to the negative 8th coulombs. As far as assumptions made in the model, we assume that the tapes had the exact same charge, despite them having slightly different lengths. As I previously said, the main point of this lab was to improve upon the data that we found in Lab 1. In the previous lab, we were able to approximate the charge of the tapes by representing them as a single point charge in their geometric center. This assumption yielded us a net positive charge of 1.189 times 10 to the negative 8th coulombs for each of the tapes. However, when comparing the charge value from Lab 1 to that of Lab 2, it's off by over 100%, as the newer value is more than double that of the old one. These values differ drastically because the point charge assumption used in Lab 1 was treated the tape as a single strong point charge, rather than a multitude of weaker ones. The model did not account for any possible horizontal forces that would ultimately take away from the strength of the electric field in the vertical direction. As a result, the charge appears to be significantly weaker than it actually was. And by using integration to account for all of the bits of charge spread out along the surface, we can more accurately find a value for the charge of the tapes. And here is the code that I used for my model. Thanks for watching.